Okay, so yesterday we went over experimental probability. Just a reminder, so experimental probability was determined by the results of an experiment. So that was the number of successful trials divided by the total number of trials. So in order to calculate experimental probability, we needed to do was conduct an experiment. Conversely, today we're going to go over theoretical probability. So theoretical probability isn't determined by the results of an experiment, but it is determined by possible outcomes of an experiment. So we calculate the theoretical probability. This time we'll write a T here instead of an E. So the theoretical probability is the number of successful possible outcomes here. Number of successful possible outcomes divided by the total number of possible outcomes. Just get a thicker pen here. Divided by the number of possible outcomes. So in this lesson, we'll be working often with a standard deck of cards. So let's just quickly go over what that looks like. So we have 4 different suits. We have the spades here, we have diamonds, clubs, and hearts. Spades and clubs are the 2 black suits. Hearts and diamonds are the 2 red suits. And in a deck of cards, each suit will have 13 cards. And these 13 cards are the same in each suit. That's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then our 3 face cards, jack, queen, and king. I think that's all the information we'll need, so let's go on. So first, we'll start with our first example. A card is randomly selected from a standard deck of cards. Determine the theoretical probability of drawing a club. Well, first we'll set this up the same way we did yesterday. So the theoretical probability of drawing a club equals the number of successful possible outcomes. So here that means the number of clubs. That is the number of cards that we can draw from this deck that satisfy this experiment. So the number of clubs divided by the number of cards in the deck. Well, if each suit has 13 cards, that means in the deck there are 4 suits times 13 cards, which is 52 cards. So the number of clubs we've just gone over, that's 13. The number of cards is 52. If I plug that into my calculator, 13 over 52, I get 0.25. I can turn that into a percentage by multiplying it by 100%, just like yesterday, and that's 25%. So let's move straight forward onto drawing a queen. So the first time we were talking about drawing a particular suit, that was clubs. This time we're talking about drawing a particular number, if you will, and this number is a queen. So in total, let's see, the theoretical probability of drawing a queen is, again, the number of queens divided by the number of cards. Well, in the deck there's 1 queen per suit, so that means there are 4 queens divided by 52 cards. And if I put that into my calculator here, then I get 0.077. And again, I can multiply that by 100%. Bring me 7.7. So there was a 7.7. The probability of pulling a queen, of drawing a queen, is 7.7%. And let's continue. Now this time we're getting a little bit trickier. So for example, 2A and 2B, we only had one requirement. The first one was a suit, the second one was a number. This time we have two requirements. The first is a color, and the second one is the number, if you will. So that means it must be a jack or a queen or a king. But also, so what we're looking at here, it's not just any of the jacks or queens or kings. What we're looking at is it needs to be a black jack, queen, or king. So we'll look at our black suits, and that is clubs here and spades here. Clubs has 1, 2, 3 face cards. Spades has 1, 2, 3 face cards. So in total that's 6 face cards that satisfy both being both black and face cards. So the probability, the theoretical probability of drawing a black face equals the number of black faces divided by the number of cards. Well, like I just said, there are 6 black faces. As before, there are 52 cards. If I put that into my calculator, I get 0.12, which I can multiply by 100% to be 12%. And finally, we're looking at not drawing a diamond. So this one's, again, worded a little bit differently, but we'll work through it. So the theoretical probability of not a diamond is the number of cards that are not diamonds divided by the number of cards. Well, if I go up here, number of cards that are not diamonds is all of them except these. That means 13 here, 13 here, and 13 here. So that's 3 times 13 are not diamonds. We'll put that in brackets, divided by 52 cards. 3 times 13 is 39, divided by 52. And if I put that into my calculator, it's 0.75, which I can multiply by 100%. So the probability of drawing a card that's not a diamond is 75%. And that makes sense. We know most of the cards are not diamonds, so we should expect a pretty high percentage there. Next, we're going to step away from the deck of cards for a moment, and we'll talk about a bag of marbles. So this bag of marbles has 12 red marbles, 8 black marbles, and 4 blue marbles. So if we're randomly pulling out one marble, we need to find the probability of grabbing a red marble. Well, I'll set that up. Theoretical probability of grabbing a red marble is equal to the number of red marbles divided by the total number of marbles. Well, the number of red is 12. Total number of marbles, we're not sure. But we can calculate that. So the total number of marbles is our 12 red ones plus 8 black ones plus 4 blue ones. If I put that into my calculator, do it in my head, I find that it's 24 marbles. And if I divide that using my calculator, I get 0.5. I can multiply that by 100%, and it's 50%. So there's a 50% chance of grabbing a red marble. Now next, we're going to look at grabbing a red or a blue marble. Again, the theoretical probability, red or blue, equals the number of red and blue marbles divided by our total number of marbles. Well, the number of red, I have that above, that's 12, and I have 4 blue marbles right here in brackets. Those brackets are important. Divided by the number of marbles, which, as we calculated above, it's 24. So 12 plus 4, because those are in brackets, we calculate those first. That's 16 divided by 24, which equals, let me see here, 0.66 repeated. 0.66 repeated. And if we're making that into a percentage, multiply it by 100%. And we can round it as well here to 67%. It is important that we round that correctly. Finally, we'll look at not grabbing a black marble. We can do this one of two ways. Let's see, actually we'll attack it just as we would of any other. So the theoretical probability of not black equals the number of red marbles and the number of blue marbles divided by the total number of marbles. Well, if I'd like, I could count those out and do the math as we have before, but if I notice, that's the same thing as we've written up here. I see the number of red and blue marbles divided by the number of marbles. And if I step back for a moment, that makes sense because we only have 3 different colors of marbles. So if they are not black, then they must be either red or blue. So this is the exact same question, just worded differently. So we don't need to do all of the math. I know it's going to be 67%. And let's keep going. We just have one more example here. If we draw 1 card from a standard deck of cards, what's the probability of drawing a spade or a jack? So this is interesting here. When we work with standard decks of cards, we'll always want to scroll up to wherever there is a picture of a deck of cards so that we don't need to do it in our head. When we work with standard decks of cards, if we do them in our head, we're going to make mistakes. So the first one, the theoretical probability of spade or jack. And actually, don't copy this here for a moment. I'm just going to show you what happens if we don't scroll up and take a look at our deck of cards. Well, I might say that the theoretical probability of drawing a spade or a jack is the number of spades and jacks divided by total number of cards. And I know there are 13 spades, and I know there are 4 jacks, and 52 cards. That equals 17 divided by 52, and if I put that into my calculator here, then it equals 0.33. But if we, so I'll just move that off to, I'll just move this off to the side here so we can compare what happens when we work without looking at our standard deck of cards and what happens when we work with it. So that equals the number of spades or jacks divided by number of cards. Now some of you may have noticed already the problem, the mistake I went through when I worked here, but we'll see by coming up to our standard deck of cards. So what we're looking for here are spades and jacks. If it's a spade, it satisfies our requirement, and if it's a jack, it satisfies our requirement. Well, that means all of the spades here satisfy it, so that's 13. and then I have 1 jack, 2 jacks, and 3 jacks. So that's plus 3. That means there are 16 cards that satisfy the requirement. 16 divided by number of cards, which is 52. And here we notice these two numbers, they don't agree. Well, the reason for that is we have 1 jack up here, the jack of spades. That one, when we performed the problem without referring to our deck of cards, that one we counted twice. We counted it as a spade and as a jack, but we can only pull it out once. It's only one possible outcome because it's only one card. So we only are able to count it once. So what we'll do here, we'll remove our, I'll leave it there for now actually. So I can do 16 divided by 52, and that's 0.31, which is 31% after I multiply it by 100%. We do notice that there is it's a slight difference, but it's enough that if you had performed the question counting your jack of spades twice, you would have come up to the wrong answer. And finally, we'll look at the black cards or a face card. So the theoretical probability of black or face is the number of black or face cards divided by the number of cards, just like last time. Well, we've learned from our previous mistakes, so we'll come up here and take a proper look at what we have to work with. So we're looking for black or face cards. Well, if I remember, my clubs are a black suit, my spades are a black suit, and then I have 1, 2, 3 face cards, 4, 5, 6. So that's 13 here, and 6 face cards. So I can write that all down in here, 13 plus 13 plus the 6 face cards, divided by the number of cards, that's 52. And 13 plus 13 plus 6 is 32 divided by 52. And if I plug that into my calculator, I get 0.62. Multiply that by 100% equals 62%. So that's how we work with theoretical probability. Note, it's a little bit more straightforward than working with experimental probability, but sometimes the only information we have is from an experiment.